Hi, this is Spencer Lee with ADAPT Software. I'd like to welcome everyone to today's webinar. Today we're going to be covering an introduction to two-way PT slab design using ADAPT-PTRC, and some of the main topics that we'll be covering will be how do we determine and select frame lines that are part of a larger slab, a two-dimensional, or excuse me, a three-dimensional two-way slab. How do we essentially take that slab and break that out into frame lines and then model that in ADAPT-PTRC? We'll talk about tendon selection, parameters, what we look at when we select tendons in terms of the design, and how do we model those tendons inside of ADAPT-PTRC. How do we model geometry? What are some of the main key points to the modeling interface and the selections to be made within the program? And then finally we'll look at some of the results in PTRC. So today's meeting should last roughly an hour to an hour and 15 minutes. If any of you need to go early, please feel free to just leave the meeting. We will record the meeting or the webinar and place that on our YouTube channel just a few hours after the meeting. So by tomorrow morning the recording should be on our YouTube channel, which is youtube.com/adaptsupport. It's under a playlist called Adapt Webinars, and we put all of the webinar recordings on that particular playlist. A couple of other announcements. If you have any questions, you should have a panel, a GoToWebinar panel that allows you to ask questions, and we would just ask if you keep questions focused and related to the material that we will present, or questions about items that pertain to the program. If you have troubleshooting or licensing questions, we would just ask that you submit those questions to our support staff, support@adaptsoft.com, or you can contact me after the meeting and I'd be happy to help out with any issues you have with the software. So we'll go ahead and begin. All of you are on mute, so if you do need to ask a question, you'll have to type it into the question box on your GoToWebinar panel. So we'll go ahead and get started. Today we're going to be looking at a fairly uncommon shape of a slab. It's somewhat of an oval shape. It has shear walls, columns, a few openings, and we want to take this slab and we want to determine how do we model a specific frame line within this slab in ADAPT-PTRC. And the intent here and the assumption is we're going to be using the equivalent frame method versus finite element method to analyze and design the frame lines that are located inside of or within this slab. So if I was to draw and highlight some of these frame lines, we're going to assume that the tendon placement will be banded tendons in the X direction. So we might have a frame line along these paths that I'm drawing or roughing in here with this highlighter, and so these might be our banded frame lines, and they're single span with a few cantilevers, short cantilevers. They're multiple span here as you get towards the inner portion of the slab, and then we get back out to single span on the opposite side. So it's fairly symmetric about both axes in terms of the geometry. In the other direction, this becomes a little more, I guess, difficult, or a little more selective on how we need to set this up because of the shape of the slab. It's not a square box, it's not a rectangle, so it becomes a bit more difficult in doing this. So we'll go ahead and I'm just going to erase the banded direction. We're going to focus on the distributed direction today in terms of setting up the frame line. So in the distributed direction, there's multiple ways. If I was to ask 4 or 5 of you, how would you break this slab into frame lines, I might get 5 different answers. They might roughly be the same, but potentially an engineer or a designer could have a different interpretation of how this might look. So for purposes of being able to model relative to the equivalent frame method in the program, we have to model along along a line of supports. So those supports can be columns, they can be walls or ends of walls, and so on, or beams. Let's say you have a girder or a beam that's supporting the slab. In this case, we have columns and walls. So one frame line would be along this perimeter, and out on the end we just assume that it's a cantilever. And another frame line would be the opposite side, something like this. And then on the interior of the slab we have decisions to make. So we might have a frame line. If this here, I mean, one approach might be to create a cantilever from this slab edge out to this column, and then to the wall, and to the wall that's in line with the support line, back to this column, and then back up to the slab, where you have this long cantilever that you're trying to satisfy. That's not the most efficient way to set this model up, because typically this support line would actually flow from a support, so it might come to this column and then go into this path and back out to this column, or we might go from this column into this path and back out to that column. So this is getting a little bit sloppy. Let me show you what we have in terms of these frame lines in ADAPT Builder. So I'm going to first show you the breakout of this slab in Floor Pro, and tomorrow we're going to be doing another webinar that's similar to this in our finite element software, ADAPT Floor Pro. But this is the same slab that you just saw. We imported it into Builder, and we'll show that process tomorrow. We imported it into Builder, and inside of Builder we set up what are called support lines. So if I look at the banded direction, and let me go ahead and just discard the design strips first, I have lines of support that represent frame lines inside a Builder, and these are really used to develop design strips in this 3D FEM program. So I have these in the X direction, and again in the X direction this is pretty cut and dry with how the support lines are laid out, but in the Y direction it becomes a little foggy in how this is done. So in this case, the way I have laid out the support lines is, again, I have support lines around the perimeter column line on either side, and I've chosen to create a support line that starts at this column here and it runs along this wall edge and then back to this column. So I'm defining the load path in this case. Now one thing that a user might do is you might choose to add an additional frame line, maybe from this column to this column. So you might add tendons that follow this path that I've defined, and you have a tendon this way, and that tendon might split and come out this way. It depends on which direction the tendons are located versus banded versus uniform, and so on. So another path we have here is this path here, and again you might have another support line that branches off and does this. So there's various ways that this can be done. We're choosing one particular load path, and we're going to stick with that load path and carry that through for the design of this distributed frame in this slab. So we'll go ahead and continue on. Now if I was to break the tributary out for this particular frame line, I'll go back over to my CAD file, and these are the tributary regions that I've generated for my distributed directions, the frames in the distributed direction for this particular slab. So in ADAPT-PTRC, I cannot model a slab frame that is bent or has curvature to it in this plane, in the XY plane in this case. The slab has to be modeled along a straight path, and it follows some of the rules and some of the provisions found in different codes relative to equivalent frame methodology. So we go in and we modify the column stiffness, we modify joint stiffnesses and connectivity based on those provisions, for example in ACI, which is what we'll be using today. So we have to make some assumptions as far as how this thing needs to be modeled inside of PTRC, which is the software we're looking at. So if I go over to PTRC, you'll notice I've modeled this this frame line. And if I go to a top view of the frame line, obviously that looks a little bit different than what we're seeing over here. It's been straightened out and we're using projected or linear or segmented, let's say, span lengths. So I've defined each of the span lengths in this case. Starting at the top, you can see I've put dimensions between column to end of cantilever, column to column, and it's just a straight line segment length between each of the supports. Okay, and in terms of the tributary, I've chosen to use maximum, let's say the maximum width for each span for its tributary. So I've simplified this somewhat. Depending on how much variance there is in a tributary, then it may make sense to segment the tributary. And I'll give you an example. Let's assume that between this column and this wall, I'll go ahead and just draw the wall here, and I have a column here. And let's assume that the tributary for that particular span actually looks something like this in reality. And so this distance from the top to the bottom, this might be 2 times the tributary down here on this end, which is T, we'll call it. And so in this case, it would be more of a gross design in terms of just approximation if I was to just use 2 times T as the tributary for the full span length. So in this case, I have to idealize this particular span into multiple segments, and that segmentation might look something like this. Here's segment 1, segment 2, you might have segment 3, 4, and maybe 2 more, 5 and 6. So the segments have to have a straight edge on each side. You can't taper the edge like what is shown here. And these segments can be input in the program up to 7 segments per span. Again, to be able to cover the material today, we're just going to assume that each span has one uniform prismatic thickness for the tributary and for the slab itself. So, but this is how something like this would have to be done if you have some severe difference in tributary one side to the other. So let's go ahead and erase that. And I'll just kind of scan through this. You can see, for the most part, the spans are pretty consistent in terms of the tributary. So the fact that we're doing uniform span width or uniform tributary width is not a gross approximation. It's pretty accurate in terms of the modeling here. And you can see I have the width of the tributary shown here. So in this case, I've actually used ADAPT Builder, which is this program, to develop those tributaries that you just saw. So in this program, I can generate tributary regions. And when I generate the tributary regions in Builder, I'm able to pull out, if I was to go to the single reports, the graphical reports, I'm able to pull out these design plans which essentially show the tributary regions that would be evaluated inside of this program for purposes of designing the strips and checking stresses for tendons and so on. So I just use this tool to generate this view showing the tributary. Now I could have easily had done this if I had a CAD file or Revit file. I can go in and use some other tools to generate the geometry, but at some point you're going to have to build a model based on that discretization of the geometry. And so now we're going to go back, taking this information and taking the slab strip that we have dimensioned here. We're going to go in and begin building this model inside of Builder, or excuse me, inside of PTRC. Now, one other comment I'll make before we start building that model is, if you have similar like tributaries, it makes sense to try to cover multiple strips with one model. So if you have a very repetitive layout where you have a lot of consistency and redundancy in terms of the frame lines, you might only have to model 3 representative frame lines in PTRC that cover, in reality, 10, 12 frame lines in a real model. It just depends on the complexity of the slab. If it's a very unique slab where every frame line is different, obviously that's going to take more time to break out the design strips and build those models inside of PTRC. So we're going to just start this from scratch, and I'm not going to focus on every input screen and describing every input screen. I will try to focus on the most important of the input screens in the program. Remember, this is more of an introduction to the program and its use for designing slabs. So that for some of you, this may be repetitive, and you might be experts in using the software. For others, you might have very little experience using the software. So let me go ahead and close this particular model, and we're going to start from scratch now in modeling that strip. So we'll go ahead and launch PTRC 2016. For those of you who use the software consistently, we will be releasing a new version, which is version 17, next month. We're currently working on developing that version, but I would like to stick with the commercial version just in case there are any issues in 17 that I'm unaware of. So those can tend to be a bit more unstable due to the development. We'll go ahead and just create a new file, and we're going to set up a two-way slab. The geometry input is conventional. There's a difference between conventional and segmented. Conventional means that every span has to be prismatic at every section within that span. So the span dimensions can change from span to span, but within the span you can't have different dimensions. If you wanted to use segmented input, which was what I described earlier, then you can have up to 7 segments for each span and 3 segments for cantilever. So there's a question. Let me go ahead and answer the question here. Okay, it looks like it might have been retracted. So if someone has a question, go ahead and raise your hand again, or go ahead and just type into the question box, and I'll pick that question up as I see it. So the program, something that was introduced in version 2016, was the ability for the program to recommend slab thickness. This is based on PTI recommendations for post-tension slabs, and for RC slabs it's based on recommendations given in different design codes. Today we're going to be using ACI, and we'll be working in American or US units. So we'll do a conventional slab input. When you go to conventional input, you have the ability to explicitly model drop panels, drop caps, and transverse beams. So we could, if we said yes here, then the program would allow us to input the different geometrical variables for those inputs. We're going to just do a flat plate today with no drops. If I do select recommend slab thickness, we'll come back to this and use it towards the back end of today's webinar, but this would allow us to see what the program recommends for a slab thickness given the span length that we're using. If you have drops that are modeled, this changes in terms of its prediction for the slab thickness, so it's dependent on this selection here also. We'll go next here. The American ACI 2014 will be used. Notice that other international design codes are grayed out because we're working in US units. If we opened it to SI units, then all of the codes would be selectable, or MKS units, those codes that or those regions that use MKS would be selectable. So this just filters out which codes are available depending on the unit system. The analysis options, these are important for people to understand. There's an execution mode that probably 99% of our users, as far as we can tell, use interactive. And I would always recommend, especially for beginners, to use interactive. Interactive means that it allows the user to review the initial design that the program comes up with in its algorithm for PT selection. It allows you to stop the recycler, review the PT force, modify the force, modify the number of strands if you're using tendon selection method, modify the profile, so you can make changes to a design and recycle that design to update the results. Automatic mode means that if the program finds a suitable force and profile that meet the serviceability criteria for PT, pre-compression, balance loading, allowable stress, tension, and compression, both for sustained, total, and initial conditions, then the program will basically exit out of recycler automatically. And it becomes more black boxish, if you will, when you're using automatic mode. So I recommend always use interactive mode. There's other analysis options. Just something to focus on. We'll be using equivalent frame method today, so that initializes those modifications to the frame and the stiffness of columns and so on at joints. When we invoke this, if I say no to this, the user can increase the moment of inertia over supports, so it includes some of that stiffness due to the column or the presence of a support there. Otherwise, it just uses kind of a pure stiffness method approach for the frame in terms of the solution. So we'll use equivalent frame method. On the other side of the fence here for design options, what's important to note here is that depending on what code you've selected, the program applies different provisions for meeting the strength requirements in terms of flexural and shear design, and also requirements for minimum reinforcement. So if you choose to disregard, this does not mean you're disregarding all of the provisions of the code. It just simply means there are 3 unique options that can be disregarded that pertain to the design of the system. So some of these may not apply. For example, if you're doing an investigation and you already know the rebar in the slab or the beam and you want to model that rebar as user-defined rebar, then you might not have a reason to have the program calculate minimum rebar for the particular system. So you would turn this off, you would disregard it. You can also disregard capacity exceeding cracking moment. This is applicable to bonded systems versus unbonded PT systems. So depending on what type of design you're doing, this may not apply to your design. And I'll actually leave that one selected. We're going to use unbonded post-tensioning today. For contribution of pre-stressing and strength check, if for example you are using PT to control deflections for a design, but maybe you're designing a slab or beam as an RC design in terms of strength, then you would check this box and allow the program only to use the PT for essentially the deflection check that the program makes. So those are explicit items that can be turned off or on based on types of designs that you're doing. One more thing I'll mention here is moment capacity, and this is something that a lot of users have questions on when they're using the software. And the first comment I'll make about this is that the program is always operating in design mode, regardless of the selection made here. If you model a slab or a beam and you add rebar, you actually model base reinforcement in the slab or beam. And let's say you're doing an investigation of an existing slab or beam, and you model the rebar that's in that slab or beam. You also model the post-tensioning that's in that system, and you say execute, and then you look at the results. If there is an insufficiency in capacity at any 20th point along any span, the program always calculates the additional rebar that would be needed to meet the demand capacity, number one, or to meet the minimum requirements, or I should say, and to meet the minimum requirements, unless you've disregarded that, which is here. So it's always operating in a mode of design. There's no real pure investigative mode where the program would never report calculated rebar, as we call it. If you wish to look at the capacity of a section or a system, rather, for only the user-defined reinforcement and the post-tensioning that you model, the program will report the capacity of that particular system, which is user-entered values for capacity, as compared to design values. This includes user-defined rebar, post-tensioning, and any calculated rebar that the program deems as necessary to meet demand or minimum requirements. So there is a difference in terms of what the program will report in this tabular report for moment, capacity, and demand, but it is always checking and adding rebar to a design if it's insufficient in those in strength and service. Okay, so we'll go ahead. We're going to do a new design. We'll keep this at design values. In this case, there are, let's see, there's 7 spans and 2 cantilevers, so I'll just go ahead and start building this model. And you'll see up in the structural view, the model will start coming into focus as we build the model. I'll stretch this out a bit. I'm going to turn on the checkbox for the cantilevers. The current design type dictates that these are prismatic. If I try to press this and change it, it won't allow me to unless I turn it back to segmented on the input screen. These will all be flat slabs. You'll notice that we could also model rectangular T-section, I or L section, extended T-section. One thing to note is if you are modeling a beam, if I go to beam system and I have effective width turned on in the input, if I go back to the geometry, the program will actually lock out I, L, and T section, or extended T section. So these particular sections are locked out because the selection for effective flange applies to a T section only, not these other sections. That's our interpretation of the provisions in this particular code. So one way to get around that is you can always go back, turn off effective flange. This just means the program is not going to auto-calculate the effective flange width, and now you have the ability to, for example, model an extended T-section, and if you go into the next input screen, you can user define the effective flange width for that section if you wanted to apply an effective flange for the beam. So I'm trying to hit on a few points that come into our support staff fairly often. So let's go back. I'll go back to 2A slab. Now, instead of going next, I can go back and just come up here to one of these tabs. For example, geometry, span geometry, and that takes me back to the input screen that I was just on. So first I'll enter the span lengths, and these are quite exact in terms of that drawing that you saw earlier. And let's see, this is 28.2, 32.1, 20.6, and 17.4. So we have a unique length for every span in this model. You could also use typical row. If every one of these spans, for example, was 30 feet, I could have entered 30 in the typical row and enter, and it would have filled out each of the spans. But here, every one of them was unique. The tributaries are also unique, so I'll go ahead and model these. Okay, and then we have 150 on the last few. And then the span thickness for each of the spans will be 8 inches. We're going to start at 8 inches for our slab. You'll notice as I entered those spans and thicknesses and whatnot, the program filled out this screen. So by default, we have these left and right multipliers. And in reality, this is a perimeter frame line. This is on the exterior of the building, so it's an exterior frame. So we have roughly 2 feet from the center line of the support to the edge of the slab, and that happens pretty consistently on each support. So we're assuming that the exterior cantilever is, let's say, 2 feet, 24 inches. And so if I look at the top view of this, this datum here, everything is modeled relative to that datum. So right now, when I enter for example, a tributary width of 150, 75 inches is placed on the left side, and the left side is above this particular datum. The right side is below it. Imagine if you were standing over here looking into that frame, your left arm and your right arm and so on. So that this is left edge and right edge. And so 75 inches on the left, 75 on the right. And that's done by use of these multipliers. We're using just a value of 1 for unity in terms of the total tributary. So as an example, if I go over here and I say, oh, I'm going to do 2 and 2. Well, that just takes 150 times 2 and it applies it to the left, and 150 times 2 here and applies it to the right. So it becomes a multiple of these, obviously, these multipliers. And so we're going to go ahead and modify these. Now, the program only considers bending about an axis out of plane. So if I was to draw an axis here, the program considers bending about, you know, this axis. So it's always just bending and shear in the plane of the frame. So if I was to go back to this view, we consider shear and flexure, basically. We don't consider axial force in this program. That's one of the big differentiators between PTRC and Builder, is when it comes to restraint, and you might have a slab that has shear walls out on the perimeter. This happens a lot with podium slabs, for example. You have shear walls in undesirable locations where when you stress the cables, if those shear walls are not detailed properly, you're going to develop restraint cracks and restraint due to the stiffness of the wall and the connectivity between the slab and the wall, and you lose precompressive force. That can be mimicked inside of Builder, because Builder accounts for the axial displacements and axial forces in the plane of the slab. PTRC does not. So in PTRC, we just assume that the detailing, the evaluation of the restraint and the cracking and how that's mitigated, that's all done outside of this program. We assume that the slab is going to be able to shorten freely, and the assumption, for example, for precompression is we're just taking the force in all of the tendons, dividing it by the section area, and that's our precompression. But to actually realize that value, the slab has to be designed, and the user or the engineer has to make sure that it's detailed properly to account for restraint. So modeling these slab panels out of, you know, if I go and change these multipliers, which I'm going to do now, you're going to see, if you look at the frame, you'll say, well, do I have torsion acting on this frame? And because now I have an unbalanced panel along that datum. The answer is no. The only reason we move the frame in and out, or in this case up and down, is so that the program can properly interpret each of the column locations for punching shear. And also, graphically, it's represented correctly compared to the main slab that we're working with. So we'll go ahead now and enter these multipliers. We have 0.16, 0.14, 0.13, 0.12. I think the rest of these are 0.16, and then we'll just, the balance of that will be carried over to the other side. So we have 0.84, and I'm just copy pasting that. This is 0.86, 0.87, 0.88, and 0.87 again, 0.85. Okay, so now I've moved my frame such that I have a exterior edge, and the main body of the slab is to the inside. So the left side is exterior, the right side is interior. And that comes into play when we do punching shear. So the only other thing I would recommend is, right now the reference plane for the slab is, again, this datum, and it's set to 0. So you can step the slab vertically downward or upward using this reference height locator. I recommend setting this equal to the slab depth, because that means that the control points for the tendons will be positive values from the soffit upward versus negative downward. And typically, you know, on drawings, I doubt many of you are referencing the CGs of the cables with negative numbers. It's just more consistent with how it's typically detailed and called out on plans. So we'll do this as 8. I'm just equating the height of the slab to this, and that just lifts the slab up above the datum. So we'll go now to the next screen here, and I'll just quickly enter the column heights. I'll say this is a 10-foot frame. The dimension of the columns is going to be, in this case, let's say 22 by 22. So I'm just guessing. Now, you'll note that I would have to enter the real, true dimensions of these columns. Now, I'm going to take a shortcut now and transition to my other model. Now that you've seen how do we get that frame data into the slab, let me go back and open my previous model, because I have the actual column dimensions in that model. So give me one moment here. We'll go ahead and open the support line. And if any of you are wondering, am I trying to play a trick or anything like that, the answer is no. I'm doing this simply to have the right supports that are reflective of the actual model. So that's if this thing saves. Let me see what's going on here. Okay, so this is the real model. Let me go over here. I was playing around with this model yesterday. Let me just make a change to the outer bays, 8 inches for the thickness. You'll see this looks similar to what we had. So these columns, the height is 9.33. We have circular columns, rectangular columns, and then we have walls. If I go back to our CAD file, we actually have a wall here and a wall over here that supports the frame line. So in my model, I just used a 4-foot width, just arbitrarily, for modeling that particular, those 2 particular walls. And you can see those walls should be shown. Let me go to a plan view again. So the wall, there's a wall here and there's a wall here. And you might say, well, why not use the full width of the wall across this slab? Remember, the wall, in this case, the wall has to be modeled as a column. So it's really only represented by one single frame element point at the reference line. So if I was to increase this to the slab width 184, you'll see it just becomes centered on that frame line. So graphically it looks wrong, but analytically everything's taken back to the center line of the frame anyway. So it's really to the user's discretion how much support width, what size of support you want to model for a given support, because ultimately the frame actions and the response of the frame is dependent on the stiffness of those supports and the slab and so on. So you may make a different decision here for this one. I'm just going to go back to what I had earlier, which is 48 inches. And let me go back to the solid view of the slab. So one thing I'll notice, or I'll make mention of here, is you can modify the stiffness of the column just as a percentage of total. The stiffness of the frame is always considered uncracked in this program. The only time it considers cracking within the main operation of the program is when we check for deflections. It automatically will always check for cracking for deflections. So the program will report deflections in terms of whether or not the slab or the beam has cracked. So that's done automatically, but the actual general analysis of the frame is based on the uncracked properties. The left edge and right edge, if I go back to a top view, this dictates how the program categorizes a column for punching shear. So for left edge, notice I've set it to exterior because this is the exterior of the frame. For right edge, I've categorized this as interior. And I'll go ahead and go back to this view. Let me erase that. I'm also going to turn off the support. So I'm using some of these quick graphical tools that allow me to more easily turn off and on some of the different components that are shown graphically. So for example, if I look at this circular column, the first thing to note when it's looking at this for punching shear, the program converts this circular column to an equivalent square column. That's number one for punching shear purposes. For determining what shape of a critical section the program will evaluate for punching shear, the program counts and relies on this input by the user. Whenever you have left or right edge set to exterior, this means that out of plane to the left and the right side, the program will make a check from the face of the column to the perimeter of the slab. It looks at this distance, and the question is that distance less than or equal to 4 times the slab thickness? And because we've set it to exterior, it triggers this check. If it's less than 4 times h, then the program discounts this side behind the column. And it essentially assumes that the face of the column is a free edge and you have a 3-sided critical section in this case, where you have an end edge condition. If I switch that to interior, the program will use that as let's say a interior edge. So it actually categorizes this as an interior condition with 4 sides, and one side is just simply truncated relative to the other side. So the program would actually give you 2 different results depending on if this is interior or exterior specification here in this input screen. In plane, the program knows what to look for. It knows that for this particular column, which is in reality a wall, it would actually check punching based on the shape. It knows that in the direction of the frame you have slab here and slab here, so you have 2 critical sections there. Out of plane, that's where these come into play. And stepping back and looking at this model as a whole, or this slab as a whole, remember you're also going to have frame lines potentially in the transverse direction, and that same column will be modeled in the other direction. So whatever design you get for the model we're working on now, whatever design you get for punching shear, you're going to have to take the design in the opposite direction and collate the 2 and determine, you know, which one controls in terms of punching shear. That's if you're relying on the punching shear within this program. So that's something to note when you're using the software. Okay, so we'll go next, and let's go back, turn on that frame, and I'll show that in elevation again. The next item is boundary conditions. So for upper or lower columns, you can specify the connectivity between the slab and column, or the beam and column, and also the base and the column. So in this case, we have a 1-1 arrangement. 1 is fixed, so it's fixed here, it's fixed here. We allow for pinned and roller supports also, so the user can modify the frame relative to those different selections. And if you're designing to face of support, the program uses this support width option for face of support. So if you enter column data, the program will just fill this in automatically relative to that data. If you deselect, you can override these inputs for support width. The slab fixity at far ends, these are currently inactive for this model, but this is really meant for a one-way slab. If you want to avoid any rotation and pure, like infinite rotational stiffness for a joint, which is pretty rare, then you would invoke these full fixity options at the left or the right end. This is pretty uncommon to see this happen. We've seen it in several models in support where a user isn't expecting a certain result, and it's usually pertaining to this particular selection when it comes to those questions related to, you know, strange moments at the ends of slabs and whatnot. So this is very uncommon to have this for a two-way slab. Loading, I won't spend a lot of time with loading. In this model, we're using 20 superimposed dead load and 50 live load unreduced. So as a user, we have multiple load types that can be added. They can be added either by drag and drop into a cell here, or if you use the second character in the descriptor for the load and you just type that in. For example, if I wanted to do a variable load, I would type in V and it would fill that in on that line. You can enter any of these load types. The program by default is set to skip live load. So when we skip the live load, the program runs through 6 different patterns of skipping. And those patterns are found in our documentation if you're ever interested in seeing how it's setting up the live load skipping. When the pattern includes live load on certain bays, it will apply this skip factor. So we'll set it to 1. When you use skip live load, the program will then result in max and min enveloped results for strength, service, and for initial condition. So this is pretty comprehensive in terms of obtaining the results for skipping. Self-weight is automatically included. If you choose not to automatically have the program calculate the self-weight, then the user has an additional classification for loading here, which is shown as self-weight. And then if I go back, it will actually delete any of the self-weight load classifications that have been defined if you select yes again. We'll go next. Concrete material. The only thing I'll mention here, this is pretty self-explanatory. If you enter a new concrete material and press tab, it won't update the modulus. You have to press enter for that to be updated automatically, or the user can just type in and override that. But just be careful of that, of entering that data. And then for the F prime CI, this is just the concrete strength at the initial condition. So we check from a serviceability standpoint, we check sustained and total loading conditions for stress, tensile and compressive stress, and we check the same for initial transfer condition of the post-tensioning in the concrete, and that has to be based on a lower value typically of F prime C. So we'll just say it's 3,700 for our design here. The program, obviously it's not a sequential or a time-dependent program, so in terms of calculating long-term deflections, we have to apply a creep factor, and the creep factor currently is set to 2, and towards the back end of today's meeting I'll discuss how this is actually applied on the deflection end. So we'll go next. These are just the materials for longitudinal reinforcement, flexural, and shear. The program for shear gives options for both studs for two-way shear or stirrups, and the diameter, material strength, and then number of rails. This is the assumed number of rails per side for your supports. So this is a little bit restrictive, meaning if you have multiple column types, if you have square, square, rectangular, rectangular, square, circular, and so on, you might have different configurations for each one of those columns. So this potentially could mean that you may have to run a model twice to get, you know, the design for punching shear that you want relative to these number of rails per the B and the D dimension of a column. 2 and 2 or 2 and 4, 2 and 3 doesn't apply to every column necessarily for a given frame line, but it does allow you to change it per side in this program. Now we'll get into the post-tensioning material. So for this example today, we're going to use bonded 1/2-inch diameter bonded post-tensioning, or excuse me, unbonded post-tensioning. And the program can differentiate between the two in terms of calculating short and long-term loss, and also how a design code considers, you know, the type of PT material you're using, bonded or unbonded. So typically for, you know, office buildings, let's say in the US, I mean, most often you'll see unbonded being used, and we'll kind of stick with that approach. For the effective long-term stress loss, or the effective long-term stress, this 175, this is an estimated lower bound value on average that you would get after considering friction losses, seating loss, those might be considered short-term losses, and also long-term losses, elastic shortening, creep, relaxation, and so on. Anything that would be considered a long-term loss is lump summed into this final effective stress value. And this leads us to use of what's called the effective force method or effective stress method, where we assume an average force that is constant along the path of our frame line, and the alternate approach to that would be the calculated force method, where we actually calculate the losses, and so you have a variable force along the length of the frame line. So I think the most common approach used again in this region in the US would be effective force method, where the user assumes some lower bound average force. They specify that force on their plans, and then the PT provider determines the actual losses and the number of strands that are necessary to meet the design force specified by the engineer. In other areas of the world, it's opposite. The engineer designs per the calculated method, and they are responsible for predicting the losses, you know, in the design. It's not to say the engineers here are not responsible or not, but it's just a different design methodology or design approach. So this value 175, if we multiply that by 0.153, then we get essentially an effective force, which is 26.7. And when I specify this value, if I use if I select the effective force method in the program, it takes this value times this as the assumed average force in the tendon. So if you want to change that, and let's say your design standard for your office might be 26 kips, you need to adjust this value. So it might be 170 in terms of the assumed loss or the assumed effective stress. So if we say next, and we'll come back to some of the tendon selections, this base reinforcement allows the user to just enter user-defined rebar, either flexural or shear. There are two options. And you can see we can model mesh reinforcing, isolated rebar. If we were doing a beam design, it would allow us to enter shear reinforcing as well. So we're not going to add any base reinforcement. We'll just select no to that. We now get into the criteria. So this criteria, these are two pieces of the puzzle when the program determines the calculated or the necessary force to meet this criteria. So the first criteria is for a two-way slab, we have to meet allowable tension and compression stresses in the slab. and we have to meet those for certain conditions: initial condition, service conditions, let's say sustained or total. And you might have other conditions that might be critical to the design of a building that may not be termed or deemed a specific way in this program, but you certainly could go in here and modify values and check a unique condition relative to the value itself versus some label that's hard-coded in the program. So notice that the initial condition is 3 square root of f prime c, and it's 2 times that for sustained and total. And this is purely coming from the design code that specifies the allowable stress. For a beam, your range might be different. You might design between 7.5 or let's say even 6 up to 12 square root of f prime c or greater than that. One thing to note is for beams, the program can handle let's say the transition zone up to 12 square root of f prime c. Beyond that, the code requires you to consider crack sections and crack properties for the frame analysis once you go beyond 12. Below 12, you can use uncracked properties, but you have to check for crack deflections, which the program does. So if you're designing a beam that is greater than your allowable stress, you've had to go up into a range, the cracking range, and it's greater than 12 square root of f prime c, then you have to do something to manipulate the actual component shape or sections or something to make that equivalent to the cracked properties of the frame. That becomes harder in the program. If you were to ask me, should I use it for that, I would probably say no. I would say use Builder, because that allows for explicit input of stiffness modifiers in order to evaluate a frame in that program. So that's just some side commentary on the use of the program for beams. For slabs, we cap this at 6 times the square root of f prime c for the allowable stress, and then we have our compressive stress limits below that. Pre-compression, this is another piece of the criteria that the program is trying to maintain and work within. So we have minimum and maximum pre-compression. Minimum is specified typically by code. Maximum is not. Maximum is more of a kind of a standard value. It might be standard per, let's say, PTI, the Post-Tensioning Institute, or other textbooks or design guides. It might be something that's internal to your office that you've had success with in designing up to a specific maximum value for pre-compression. Typically, maximum value is an indicator of the economy of the design. So if you have a design and you're getting 300, 400 PSI for a two-way slab or plate, that means you're having to cram a lot of PT into the slab to try to meet the allowable stresses, 6 square root of f prime c. And so if you're kind of encroaching on that upper range, it's just an indicator that, you know, maybe we have to increase our strength of the slab. Maybe we have to increase the slab thickness in a certain span or multiple spans. So this is what the maximum value is used for. When we design a slab and this is exceeded, that doesn't necessarily mean the design is bad relative to the requirements in the code. It just means whatever that limit is that you imposed on this design is not met, and you can always come back and change this if needed. You know, if it's close, if let's say you set it to 300 and it's 310, well, 310 might be a fine. You know, you're working under certain constraints. You'll have to live with having that much pre-compression. So from a programmatic point of view, to have the program say okay versus no good, I would come back here and modify that value and then rerun it, and it's okay. So balance loading is another item that it's more of a design tool than anything. It was introduced long ago in designing post-tensioning. It's a great design tool to use. However, sometimes balance loading just simply cannot be met, especially on the maximum end. Again, if you're working in a zone where you're pushing the limits of a design and you have so much PT in a slab necessary to meet the stresses, the allowable tension and possibly compression stress, your maximum balance loading might be exceeded. You might have, you know, over 100, 110, 120%, and if you try to limit the design based on balance loading, then you're likely going to go back and find that you have an exceedance of the actual code-driven requirement, which is the allowable stress. So it becomes somewhat of a balancing act in designing slabs in this respect, especially when they're already on the upper threshold of these limits. The program imposes maximum spacing between tendons. This is for like distributed tendons, 8 times slab thickness, and that can obviously be modified. The design method, if we use force selection method, this is what I was terming effective force method. If I change this to calculated method, then the program allows the user to input information relative to the friction loss and also the long-term loss. So the program would calculate the losses for us if we use this input. One thing to note is if you actually switch to calculated force method, the program will give you the ability to use either force or calculated force. So this is more comprehensive if you use this option in the input. It doesn't mean you're forced to use it. It just means you have the ability to use either when you get into the recycler. So I'll just leave those as they are. We have to define profile shapes and types. By default, the program gives 3 tendon inputs, the ability to model 3 tendons. Tendon A always goes from end to end. Okay, so you always have a tendon that runs the full length of the slab or all of your spans. Tendon B and tendon C can be anywhere as long as they are within one span. A span is not, a cantilever does not qualify as a span, so you can't put a tendon like this or a tendon like that. It has to go back at least one full span. These are what we would call add tendons. So let's say you have a design where you only want to cantilever, or excuse me, you only want to post tension these end spans in the cantilever, but you don't want tendons in spans 2, 3, up to 6. You would basically set tendon A equal to 0 in the recycler, and then you would be using only tendons B and tendon C. These spans in effect become RC spans, and these 2 outer spans become PT spans. So if you want to eliminate tendon A from the design, you just set it equal to 0. If you don't set it, let's say you set it to 100, that means you always have 100 kips of force in the entire set of spans or cantilevers in the model. So for each of these tendon types, we want to define a shape for each span. So for tendon A, B, and C, we can define reverse parabolic, partial, etc. in this table. For the anchorage of add tendons B and C, I'm going to draw a slab here. So if I have a slab and I have a column here, and this is like to the outer side of, let's say, this end of the slab, and then over here we're going to anchor that add tendon behind this column right here. And the anchorage of that cable, we have to know where to anchor it in the depth of the slab. So you have defaults as to the dimension behind the support to that anchor, and that's currently set at 0.2 times the span length. It can be modified not only here but also in the recycler, and then you also have the ability to tell the program how to handle the shape of that tail. So by default, the tail will always be a cantilever down shape, and you can either say force it to be anchored at the centroid of the slab so that you don't induce a moment, or just follow the parabolic shape of the cable, and it just basically the location of it is a function of the shape of the cable, and that means it may not be at the centroid of the slab. So typically we would anchor it at the centroid for the add tendon. Okay, we're just at 2:04 p.m. my time, so we've gone about an hour. we have probably roughly 10 to 15 more minutes. Again, those of you that desire to stay, feel free, and those that have to go, I understand. So we'll just continue to plug away here. Cover and CG, I won't really harp too much on this. These are just the default CG values for the cables. We're going to use 1 inch on interior spans and 1.75 maybe for fire rating on the exterior spans. And then for cover, this is the assumed cover from extreme fiber to the face of bar for longitudinal bars that the program calculates. We'll use the defaults here. Cutoff lengths, this just allows the program to determine at what length the calculated rebar is cut off at. And these would be considered kind of default values. If you wanted to customize how the bars are laid out in the spans, you could actually override the defaults here by using curtailment. And this is just a table that allows you to define long and short bars, cutoff lengths for those bars, and so on. So we'll set that to none. We'll go back to the default cutoffs. And then finally, the combinations. Now, in this case, we're looking at only gravity loads, not lateral. The user does have the ability to enter lateral moments and combinations for evaluation of factored load combinations for gravity plus lateral. And that's shown here. You can enter joint moments that might come from a different analysis program that you may want to add. So for the load combos, the program evaluates 2 strength combinations. By default, there's entry for 4 if you needed to enter more. You have your reduction factors, strength reduction factors for flexure and shear, and then also there's 2 service combos. One of the combos is considered sustained load. That's shown here. This is a sustained combination where we're only including 0.3 times the live load and 0.3 times the X load. We have no X load in our model, so we're only using 1/3 of the live load. The total load is just all the service load. And then finally, we have a combination for initial that includes all of the self-weight and 15%, let's say 1.15 times PT. We're basically adding back in the long-term loss due to the PT because at initial the PT hasn't experienced all of the long-term loss. So we readjust that by use of the factor. Okay, so that is the input for the model. Now the next step, we're going to just run the model. So now we want the program to tell us for this particular frame line represented by this tributary, tell us how much PT the frame needs. Okay, so this is the easy step. At least at the beginning, we press execute either here or by use of the icon, and the program goes through an algorithm to determine how much PT is necessary to meet precompression, balance loading, and allowable stress. And in some cases, that the program cannot find a suitable force and profile to actually meet all 3. And I think that's what happens in this actual model. So let me close that. So we get into what's called the recycler screen. And we look at this screen, and usually those who are exposed to this as a first-time user or beginner, this looks a little bit overwhelming because there's a bunch of numbers and a bunch of text and words, and you don't know where to start. Well, the first thing I would do is just get yourself familiar with what the program is reporting. And I'll go through each of these tabs. There's the tendon force and height, and the program is essentially showing you for tendon A, B, or C, this is the selected tendon, you have the current tendon status and all tendons. If you only have tendon A specified, which by default the program only specifies tendon A, it doesn't automatically do add tendons. The user has to manipulate to include tendon B or C. So the current PT force that the program has calculated is 652.8 kips, and that's for tendon A. And you'll notice all tendons, if we sum the force in A, B, and C, we get 652.8 because, again, there's no force currently assigned to tendons B and C. If I click on tendon B, it's 0, and if I click on tendon C, it is 0. And also, one thing to note is if I go over to tab 5, tendon selection and extents, notice tendon A runs full length, tendons B by default only runs one span plus the cantilever, and I can always press Control and slide that to other spans. Once I make a change, the program automatically forces me to recycle, and it actually recalculates the result based on the change that I made. In this case, the change was inconsequential because I didn't set a force to tendon B. So I get the same design as I started with. So for tendon force and height, the program will give me this force, but it will also take that force and break it into a force per width. So for each of the span lengths that I had dictated in the geometry, I get 51.9 kips per foot, and so on, down to 52.2 kips per foot, or it reports in a number of strands. There's 25 strands in each of the different spans. Now this is all based on multiple tendon path. This means that I can specify tendon A, B, and C, or I can specify A and B, or A and C, or B and C. So I have a combination of different tendons to play with in Recycler. If I use single tendon path, then single tendon path eliminates tendons B and C, and this is actually easier, I think, for first-timers who are using the program. This allows me to actually enter different values in tendon A. So I could say, well, this is 500 and this is 300, 400 down to 400. So instead of actually modeling tendons to represent and to calculate the tendon force, you're just directly modifying the force for each span. And sometimes users prefer this method because it's just easier to change tendons this way than to actually model them. So we'll go back and I'll recycle again. I made a change. The program triggers the recycle button, and I'm back to the recycle. So I get back to that original design. The P over A gives a status of current precompression. Percent balance gives a status of the balance loading as a function of the total self-weight and dead load. The control points that define the geometry, the high and low points of a span are given in this table. And then for all tendons, we show, again, total force, the force required for each span. This is an important table here, total P over A and total dead load. So the required force comes from one of three different criteria that controls. And if I go over, I'll skip 2 and I'll go over here to 3. And we have basically, again, 3 criteria. We have P over A. This is the force needed to meet the minimum precompression, which was, I think, 125. This is the force required to meet balance loading, and this is the force required to meet stress conditions, allowable stress. And whatever controls at each location, left, center, right, for each span, the program will place in this required box over here. So that is reflected also over in tab 1 in this box here. Now, tab 4 is just a current status of stress under sustained load, total load, and this is a function. This is like output in terms of F prime C, a multiple of F prime C. So the limit is 6. You can see here I'm actually over the limit. This is 7.238, and then I have my compression stress values, and the allowable stresses 6 times square root of F prime C and 0.6 times F prime C in compression. So it shows me the actual stress versus the allowable. and that is shown for each of the load combinations. Again, 5 allows me to modify the tendons. But now what we'll do is we'll look at the status bar here. And this is where a lot of people migrate when they're designing a slab using the program. They say, oh, well, we have a problem. There's the maximum pre-compression is no good, and I can see where this comes from right here. These 3 spans, well, actually all of the spans have pre-compression that exceed 300. Okay, so the maximum P over A is no good on every single span. And the stresses, the tension stress is no good on span at the last support between 7 and cantilever right. We saw that in the stress, extreme fiber stresses under total, this is 7.28 and the limit is 6. So now, because the program couldn't come up with a suitable solution to meet all 3 criteria in all 3 spans, there are certain stopping points that the program will basically exit and give you the results in this condition. So now it's up to the user to define and determine how this needs to be modified. And if we look at this design, we say, okay, the last span and right here, right span and, or excuse me, cantilever right and cantilever left at their support have requirements that are roughly 2 times the maximum requirement for all other spans in terms of the force. So that means that we're going to model tendons B and C to customize this design. So the maximum force between spans 1 through 7 is about 400 kips right here, 400. And that means we need an additional 300 kips to satisfy cantilever right and cantilever left. So as the user, what I'm going to do is I'm going to use tendons B and C to optimize this design. And we're optimizing it manually at this point because of the end result here. So I'll go ahead and go over to tendon A, and I'm going to set this force to 400. So right now I have 400 kips in each of the spans, but now I'll go to tendon B, and I'm going to set tendon B to 300. And that fills out cantilever left and span 1. Those are linked. They have to be linked in how the program operates. And then this will be 300 also. So you'll notice over here, for all tendons, the force is 700, 700, 400s, and then back to 700. And that means we have 2 add tendons, tendons B and C, on the outer frame, outer bays of the frame. And I'll recycle that. And when I recycle that, something changed. I went from P over A maximum to being no good, and it's still no good, but now I've exceeded maximum balance loading. And looking at the balance loading percentages here, you can see this balance loading for this span 1 is 95%. I think the allowable was 90. I think I input 90 for allowable. And span 7 is also 90, 91, and 95. And the reason that those are high now is because I was forced to add 300 more kips in those spans due to how the add tendons are modeled. And because I added that 300 extra kips and I kept the same CG, my balance loading has increased. So now what I'll do is I'll just change this back to, let's say, either 5 or I'll say 6. So by changing that, I'm going to reduce the balance loading, but I'm going to increase the tension stress at those locations. Well, if I go back to my stress check and I look at the stress for span 1 and span 7, right now there's 0 tension stress. It's fully pre-compressed. So by raising the tendon, reducing the compensating equivalent load from the PT, it's not a big issue because I'm already fully pre-compressed. And we'll go ahead and recycle. Okay, and now my balance loading, let's see here, the minimum balance loading is no good. Looks like it might be this span here. I thought I had set it to 50, but I can't recall off memory. So we'll just assume that's okay. Ultimately, we could go back and tweak the balance loading for these spans. That's an easy fix. The one that will continue to stick with us really is the pre-compression. These outer bays, spans cantilever left 1 and 7 and cantilever right, those are likely going to continue to be up in the 500s to 600s. So the next step, which I'm not going to go through at this point, would be to modify the geometry. And if you can't modify the geometry, then there has to be some justification for using balance loading that is that high, and potentially extra rebar or other detailing requirements to satisfy that much pre-compression in the slab. So one thing we could do in this case is we could go back to the input, increase the thickness of those outside cantilevers, and come back to this, and we would get a different design because now we have a different input in terms of the geometry. But we're going to say, just in conclusion, that this is the final design. I'm going to exit the design, and the last thing that I'll talk about is the deflections, and I'll quickly show reinforcement for the slab. So I'll start with reinforcement. Once we exit the recycler, the program will go into two processes on the back end. One is calculating the reinforcement, and then the other is determining the deflections. Both of those are dependent on the final outcome of PT. That's why we have to solve the PT first, and then we solve the reinforcement. So for reinforcement, I'll focus on the summary to look at reinforcement. But if I go to the builder sum module, the program breaks this into multiple load combinations and also envelopes. So if I look at service, let's say service 1 max combination, and I look at the reinforcement, at the top of the slab, for a two-way PT slab, the amount of rebar is prescriptive. You're always going to have top rebar at each support. So that will not change depending on whether you're looking at service 1 or service 2, max or min. For bottom reinforcement, the amount of reinforcement is actually relative to the stress in the positive bending region. So depending on the level of stress, if it's less than 2 square root of F prime C, we don't need reinforcement. And you can see here there's actually no reinforcement required for this condition. If I look at service 2 max, we may have bottom reinforcement there, and there's still no bottom reinforcement here. So looking at the stresses for these particular combinations, if I look at bottom stress, you can see this line separates tension above, compression below. This is fully pre-compressed, so therefore I need no bottom reinforcement. Now for strength, I may need bottom reinforcement. So if I go to the strength combinations and look at those would give me an indication of what reinforcement is needed to meet the demand moments for the frame. Ultimately, we want to know the output for the entire slab, so I'll go to envelope, and this gives me an indication of top, bottom reinforcement, the final profile of the cables, the forces in the cables, and then there's a punching shear outcome shown as well. So we need, for example, we need to reinforce at columns 1, 2, 4, and then the last 2 columns on the opposite end. Those require reinforcement. The program will report that reinforcement based on the input for two-way shear. There's a secondary sheet here that shows deflections, and this is really just a mirror of the deflection report in the report generator. And the way that the program checks deflections if you recall, there's two blocks. There's two blocks of deflections. There's service load combinations and total load combinations. Or excuse me, there are sustained combinations and total combinations. There's 2 and 2. 1 and 2 are sustained. So here's combination 1. 3 and 4 are total. For each of these conditions, the program checks the deflection in stages. So if I outline this, the program will check stages 1 through 5. Stage 1 is self-weight, stage 2 is self-weight plus, and this is going to look a little sloppy, plus PT. Stage 3 is this plus SDL. Stage 4 is that plus live load. Stage 5 is that plus X load. For each one of these 5 stages, the program determines whether or not cracking exists for the system, for beam or slab. And it's dependent on whether or not the applied moment for the given stage exceeds the cracking moment. It takes into account the precompression that would have to be overcome to reverse the slab and get it into tension and exceed the modulus of rupture. So the program checks for each of these stages whether it is cracked. It then takes those deflection results and it itemizes them here. So for example, this dead load, this is really self-weight. This is the result for stage 1. Dead load plus PT is the result for stage 2. Dead load plus self-weight plus PT is the result for stage 3. And then we apply a creep modifier onto that result. So we take the creep factor plus 1, or we take the instantaneous deflection due to the sustained load plus the creep due to that same deflection, and we essentially get 1 plus creep factor that gives you this value. So if you take 3 times 0.73, you would get this value here. The program itemizes the live load deflection by taking stage 4, which is here, minus stage 3. So you get some value of deflection here. Because this is a sustained load combination, remember combination 1 is sustained, the program will take 0.3 times the live load deflection, multiply it by the creep factor, which again is 3, and it will add it to this number 2.18, and that it becomes your sustained deflection. In this case, we have very little live load deflection. And I'm wondering why that's 0, but I'll have to go back and look at that. There should be some number here. So the program, this sustained deflection includes the portion of sustained live load with the creep factor applied to it. The total deflection then takes the difference. It takes the remaining 70% of the live load deflection and adds it to this number to give you this value here. And so the program is using the live load and its sustained portion in calculating these deflections. For the total load combinations, the total service, the program ignores live load as being part of sustained, and the same approach applies. So that is how the program calculates the deflections for this particular slab. Again, I'm not sure why the live load was not shown there. So that will conclude this webinar. I appreciate everyone sticking in there and waiting on me to finish that. I know we went a little bit longer than anticipated, but at this point I'll open it up to any questions. I'll wait 2, 3, 4 minutes for any questions that come in. And again, I appreciate everyone's participation. As a reminder, the webinar will be placed on our YouTube channel, youtube.com/ADAPT-support, and it will be placed under the ADAPT webinars link. So at this point, again, I thank you, and I'll wait for any questions. Okay, looks like there are no. Someone is raising their hand. So Giordano, if you have a question, go ahead and just type that into the question box. Okay, looks like there are no questions. If you need, well, wait, just one just came in. Let me go ahead and see what this says. Okay. What would you suggest to fix those two cantilever deflections the program showed? Thicker slabs? So, yeah, I mean, thicker slabs or different material. Let's assume the loading can't change. Then you would model a thicker slab if that's if that's architecturally acceptable, which is sometimes common that it's not. Or it might be a combination of a thicker slab or and an increase in the material strength. You can also sometimes get away with tapering a slab. So if you wanted to taper a cantilever, you could break it up into segments and input tapered segments for a given cantilever. So that might be more pleasing to the design than just a solid, rectangular prismatic span on the outside. The next question is, I need to do 2 stage stressings. Is there a way to do this in PTRC when analyzing a two-way slab? Do you have? Okay, so the next question was stage stressing. Is there a way to do stage stressing in the program? There's not a way to set up multiple stages to be run in the same sequence in the program. So in order to do that, you would have to use multiple models where you adjust the loading and potentially the combinations for stress checks, and you would have to basically run multiple loadings that are reflective of each stage in the program. It's something that comes up a lot, and we do have it on our, I would say, short-term list of things to include in the software is the ability to set up multiple stages. Thanks, Fisher, for that question. The next question is, when analyzing a two-way slab, do you have to add deflections from each direction to get total deflection and midpoint between the columns? Let me answer that just in one moment, Jacob. There was another question. Could you repeat the YouTube address where the seminar will be posted? Yes, it's youtube.com/adapt-support, and the playlist is called Adapt Webinars, and that was for Henry. Henry, that's where you can access the recording. There's also other tutorials. There's a beam tutorial on the same YouTube channel. There's another playlist called ADAPT-PTRC tutorials that you can access for additional resources to learn and use the program. So back to the deflection question, Jacob. He asked if you have frames, intersecting frames, and we want to get total deflection, adding the 2 deflections would probably be conservative. It might be a situation where you take square root some of the squares for maximum deflections in the panel. You also have to be careful for balance loading, especially when you have intersecting panels. If you set the balance loading to 100% for both, and they're both right at that upper limit, then in reality there's probably more balancing than you want, so you want to make sure you adjust for that in each individual frame. That's why a lot of times you'll set it down to like 85, 90, sometimes even lower for those load balancings, and that's something that is directly handled in a program like Floor Pro versus a 2D program like Builder. Okay. So we'll go ahead and conclude there. If any of you have more questions, please, again, feel free to contact us at support@adaptsoft.com. If you need a PDH certificate for this session, please email support@adaptsoft.com. We issue those to those who send a request. Otherwise, we don't issue them. So if you need that, please let us know. Again, I appreciate it. Thanks for your time.